Good evening, Phobos. How are you? Let's see, where did I leave off? Hello. Great. I hope you're great too. Just doing some O notation work. That's been killing me. Interesting. Yeah, O notation. Is that like oh, little O? Big O? We co-working tonight. Vice, I haven't seen you in a long time. How you been? You been okay? You still playing Unite? Let's see, what was I doing here? Big O, little theta, little theta, big omega. Oh, right. I forget there's also the theta stuff and omega. Interesting. Not okay studying a lot. I'm playing a few games this season. Oh, you're studying? What the heck? How's that going? I mean, not okay, but like, what are you studying if you're okay to share? I don't know if you actually you probably don't know this because I haven't really disclosed this, but like this season, I got to masters like with 56%. So it was rough for me. Big O, little O, theta. I think like I feel like theta, if I remember correctly, and omega was like uh I feel like it was like a subset or something. Like it captured big O or little O. Or maybe I'm wrong. Ran Herald of Measure Theory. Man. You know, last night when I played, I was like I was man. I played Resi like the time I played Yu-Gi-Oh again before, and I was on it. Like my combos were like, I think my combos were like almost perfect. And then yesterday I just like a noob again. Like if I was playing the Herald again for the first time. I don't know. I guess it just depends on the day. Theta is the intersection of Big O and Big Omega. Yeah. I remember there's like a like some sort of containment going on in like intersections. I think Omega was like, um, man, I don't want to look it up. I want to like try to remember off the top of my head, but I don't think I'm going to. I remember learning about it, and I was like, oh, if you're big, if you're if you're Omega, then you're Big O or something like that. Doing your doctorates in med? Oh, dang, that's intense. That's crazy. Takes dedication. Crazy indeed. Well, good for you, Vicey. Nice to know we have a fellow um a fellow I guess I don't know how to say this, but higher education. in the Unite community. Actually, I think it was a meme at some point where there was like a PhD thing, a PhD thing in the streamer category for Unite. I remember there was a meme going on around that. A fellow cringer. Oh man. Well, how many more years do you think you have left? I see. A PhD is a commitment. Joseph. You know I love that button mash emote. Imagine if the PhD students stopped defending and got in on got in the offense. True. A lot of time. I have 2 more years to be a doctor and then all the residency. Oh no. Yeah, that sounds rough. Holy moly. It will all be worth it. Why are you asking this question? Did you not read my dissertation? Exactly. That's how that's how every defense should begin. Um, did you read my dissertation? Let's see. Joseph, you don't play Unite anymore, right? I think you said you stopped playing. You only kind of know what's going on from like either watching my stream or maybe the occasional other streams. Yeah, it's rough out here, man. It's a rough life. It is rough out here. Okay. All right, I'm about to go through something that is gonna make me a little nervous because it's like a really weird concept, but gotta go through it at some point. I've already gone through it once in another book, but this book is kind of like a little bit different. Just gotta remember what the heck I was doing. Some of these days are tough because it's so easy to rank up. I know. I think that's also kind of the case in League. That's what I've been hearing. It's become a little bit easier to get up to like the high elo. But like just a competitive, I think in competitive games in general, it's just I think they're making it kind of like accessible. In Yu-Gi-Oh, I found out in Yu-Gi-Oh, um, it's not that hard to get to the highest rank, which is Master. you just you just have to kind of have you just have to play enough games and obviously not be not be clueless. So maybe I'll grind a Masters this season just for the funsies. Okay, I was doing this. Okay, so there are some drastic changes between the book that I'm looking at on my PDF, which is the 5th edition, and the 4th edition, which I have the hard copy of. And I liked the 4th edition's um, the 4th edition version of this chapter. So I'm going to follow this more closely. But basically, I am around here, about to start Vitali, which is basically the thing that shows us that not every set is nice. Works the way we want it to work. The heck is this? Okay, I did the lemma. Okay, the lemma was basically saying if E is bounded, and we can translate E by some bounded set of some infinite set of real numbers, then the measure of E is 0. Okay. That's this thing here. So if E is bounded and measurable, and if we have oh, it's also bounded, but it's countably infinite real numbers. And if we translate them, translate the set E by the elements in this, or no, this set is disjoint. Oh, so we're constructing the disjoint set from the translations. And if this is the case, then we get the measure E has to be 0. Okay. I did this. So the order of this book is sometimes kind of awkward. I don't think it's proven this before, so I did this, and I'm probably going to put this in an earlier set of notes at some point. It doesn't even give this a proper definition. Where is this at? This is right here. It's right here, rationally equivalent, but this is like my biggest gripe with this book, is that it doesn't give like a nice, clean, like this is the definition. It's like it's sometimes in the middle of a paragraph, and the font is like so hard to distinguish sometimes with bold. So it's kind of easy to miss some definitions in this book. So a rational equivalence relation on E is defined for any non-empty set E in the real numbers for X and Y in E to be rationally equivalent provided that their difference is some rational number. So any value in E, any two values in E that whose difference gives you a rational number is rationally equivalent. And then I went and showed that this was axiom equivalence relation, which is basically showing these three properties. So not written in the book, but just I've done for fun, I guess. Now that I got rational equivalence, what else do I need? I need to. I'm gonna define the axiom of choice soon, because it's kind of written right here. Okay, clearly this is an equivalence relation that is reflexive, symmetric, and transitive. So that's literally what I just proved. We call it the equivalence relation on E, the rational equivalence relation on E. For this relation, there is a disjoint discomposition E into collection of equivalence classes. For this relation, there's a disjoint decomposition of E into the collection of equivalence classes. So basically what they're saying is that we can break E into pieces, break E into pieces. We can break it into disjoint pieces. And basically the pieces are a collection of equivalence classes. I'm thinking specifically the rational equivalent class, the rational equivalence relation on those sets. What do I set for the rational equivalence relation on E? It's a set C sub E comprising exactly one member from each equivalence class. Okay, so this is guaranteed by the axiom of choice. So this is where I have to define it. Okay, first we should define the choice function. We're at 2.45. How do I write this F? I feel like this is redundant. A choice function f on this. I guess if you call it a function, isn't it implied that it's a function? Choice function? I guess it's not. Okay, to the union, f. My gosh. I'm gonna exaggerate this a little. Oh, I hate it when my definitions spill over to the next page. A member of F. Okay. Actually, I can make this a different color. Let's see. The heck? Okay, so the axiom of choice basically tells us there's always a choice function. Okay. Can't read the noiculus. Thanks for following. Hopefully I didn't butcher that. Good luck. Thank you. Thank you. All right. What is this saying? All right, this is the thing that I need to kind of hurdle over. There is a disjoint decomposition of E into collection of equivalence classes. I think this is fine. So basically what this is saying is, what this is basically saying is that if we have E, so if, trying to think of how to say this correctly. So if basically if we have a set E if we have a set E and R, let X be an E, then then we can construct, basically, we can construct a set of, basically a subset of E. Then we'll call it, let's call it, A? So let A be the set such that Y and E is rationally equivalent. Rationally equivalent to X. So basically we can define a set A. We can define a set A that is containing X and all of the elements Y and E that are rationally equivalent to X. And that's basically building the first set. And then you can continue this process for all of the for every element in E. So how do I write this? We can just write it by referencing every element in E. I think that's fine. So it's going to involve a union. So we can actually write E as a union of these sets A. And I'm going to write this as like it's kind of like a cursive A or some shit, or some sort of like A that stands out. So this contains all the sets. Call the sets A such that if such that for every x and e, so for every x and e, KK. Are you streaming? The heck? Pretty sure you are. Should I put here? Put one of these. So A is a set of elements in E. Okay. I don't know how much clearer I can be about this. I don't know if it's obvious that you can actually construct E from these sets A. Because basically what you can do is you can first pick an element in E, and then A is basically all the other elements in E that are rationally equivalent to X, and then what you do is you pick another element in E that's not in A, or you pick an element E that's not in A. So what you would do is this is how, I mean, this is off the top of my head how I would kind of construct it. This would be then let x prime be in E minus A. Let A prime be a subset of E. Such that y prime is in E, such that y prime in E is rationally equivalent to X. So that's how I would construct this. So maybe I could put this in the middle here. Wait a minute, did I do that right? Then what we can do is you can just continue this. Continuing. Continuing like this. You construct E as a union of those sets A. Delete this. And I'm gonna write this, I'm gonna treat this as a note. Okay. I think that's good. But now, I don't understand anything. Is this what the fine print of accepting terms and agreements look like? This is what it looks like when I read it. Let's see. I'm in the scary territory. I spelled territory right? I'm not a. I don't. The joke is that I'm a mathematician, not a what's the word? Not a speller. Okay. Yeah. Okay, so I realize this thing kind of looks blurry on my stream. And figure this out. Okay, so I kind of loosely gave the argument of how to construct E from um, rationally equivalent or sets that contain rationally equivalent members. I think now what I can do is I can show they're equal. Ooh, I don't know if I want to do that. So I would have to show they're equal and disjoint. And I think it's important that they are shown to be this way because that's kind of the purpose of Vitali. Like that's like the crux of Vitali's theorem. So I think I should show this. Okay, let's make this like a result. So one of those details that I think honestly should be in this book. And it shouldn't be like an undergrad thing. This is like result what 247. If E is a subset of R, if E is a subset of R, then then E is equal to the union. All the A's. I'm just gonna copy this, you know. I think if I were to do this, I should be a little bit more better about my the way I define things. So let E be a subset of R. And let this for each x in E. Okay. Then break this down to two things. Make E as a union of all the A's, and two, A and B and the set A intersect B is empty. That's basically what we want to show. Just a little bit nervous about the way I define this because I'm literally defining it on the on the fly. I don't know if there's a way to define this, or is there if there's a way to define it differently. Okay. Oh no, our proof is on the second page. Okay, so for one, XB and E. The Pop Nemo. How you doing, baby? Okay, I need to. Okay, the XB and E. Sleepy? You gonna take a nap? Collection A is a collection of sets I just have for each. I just woke up from one. Okay. Since copy and paste. Oh my gosh, what is this? I'm starting to hate this app. Since copy, okay, copied. Copy. Okay, good, good. I think my definition's fine. Okay, since fancy A is a collection of sets A, such that E for each x and E is the set of elements in E that are rational equivalent to x. What was it? Hey, Penn Center, thanks for the raid. See, you're finished. Hey, fam. How's it going? Guys, if you don't already know, which I'm sure everyone is already familiar with, Penn Center is also a math streamer. Please give him a follow. We're finished discussing geodesics on the sphere? No way. Hey, Jeff. Thanks for the bits. And welcome. Yeah, Penn Center, also a great math streamer, does math help, does calculus, does algebra, and go follow him if you haven't followed him already. Do you take audience questions? I take I take audience questions for the stuff I'm working on, I guess. This is measure theory? Yeah, it's measure theory. Right now I am doing the unmeasurable set. Or the non-measurable set. So deriving the geodesic isn't measure theory, I assume? As far as geodesics, I'm sure it's related in some way, but or no, not in the proximity, at least at this point. This is measure theory. I'm doing the non-measurable set, which is usually basically shown through Vitali's example, which is what I'm about to start. What level of knowledge do I need to understand this level of wizardry? You need set theory and you need undergrad real analysis. If you have those two, then you're all set. Geodesics, did we learn that in DG? Yes, we did. We learned it. We touched it. I took real analysis, but no set theory. No set theory? How the heck did you do real analysis? That's insane. I must have blacked out. Are you guys memeing? Did you guys actually do geodesics and Penn Center stream? That's insane. Where can I find a good source for real analysis? There's lots of good sources. Oh, your degrees in mathematical physics, real analysis was my elective. Oh, that's neat. I actually wanted, before I decided to do my master's in mathematics, I was contemplating on doing a PhD in mathematical physics. So that is that hits home for me. We touched on it at the end. A pen didn't derive it using calculus of variations. So make Ren get his awesome library out. I do have recommendations for real analysis if you're interested. Let me see. This book right here by Terrence Tao. I actually only found out about this recently. This book is fantastic if you want to learn real analysis. It's very well written. It actually constructs the real numbers from like the natural numbers, and it's really cool to see. He also tells you when he's being informal, when like to kind of give you a little bit of awareness. Yeah, honestly, I never expected. This is not like a slight at Terrence Tao, but I almost never assumed that like the the highest caliber of scientists or mathematicians can write like a book for like a wide audience, not just like the more brilliant students. But I've kind of skimmed through it, and it's really well written. Like it's explained, a lot of things are explained in detail for like I think most people to understand. It explains why do analysis. So here's like a lot of examples that he gives about why you should learn analysis. A lot of things like that we kind of take for granted, like switching the summations for infinite sums, interchanging the integrals, why that isn't always possible, interchanging limits, why that's not always possible, um, the interchanging of the derivatives. Like it goes through all of these examples in a tangible way, and I think that's a very good, like, a good motivation for the subject. So I would definitely recommend this book. I would also recommend this book. This is like very beginner friendly, and it's very well. I like the format of the book. Like a lot of things are very like they're boxed. It's very clean in my opinion. Let me see if I can like like I mean this is what I mean by they're boxed, but there are like examples of um of like properties, I guess. See if I can find it. Like this is awesome right here. How he creates a table about properties of a sequence of functions. Koshi looks like Putin. I honestly missed the picture. I roughly saw it, but I didn't really pay too much attention. I didn't mean to distract you from what you were doing. No worries. Like honestly, if you guys coming here to chat, that's like more than welcome. I'm not. I'm doing this for fun. Like I'm going through measure theory just for fun. There's no like time pressure constraint that I'm looking at. So if you guys want to chat, like that's I'm always like open to chatting. I read Koshi. I feel so sick. Um, so this book is also good. This is a very good like good self-study book. Just a good book overall for like an introduction to analysis. This is the book that I used when I took this class. This book is actually also really good. In fact, when I ever reference analysis stuff, like if I need to like reference stuff from analysis, I look at this book because it's the one I used. So it's like the most familiar to me. Yeah, Jay Cummings also wrote a proof book, also really good by the way. It's they're very fat books. They're very thick books, and he's basically writing it so that it's like a self-study book, basically. Yeah, those are my top three recommendations. I hope that helps. Yeah, so I'm working through this. This is like a little nerve-wracking because I remember going through this example in my other measure theory book when I went through it, and it was confusing. I think when I worked through it, I kind of understood what was going on. You're basically kind of like picking out things from a set and like keeping um basically like the irrational parts. Was that the app library with this one? What the heck? This is for like the iPad. I put all my books on the little on that book app. Probably not the greatest, but it's what I've done from the very beginning, so I'm just whatever. Okay. So I need to prove this. And this is kind of like the the most important part of the Vitali theorem. Like this needs to be true. I got to get my iPad up and running like yours is. Looks great. You mean like with the books and stuff? The notes? Because the percentages feature of how much of the book you've seen is pretty nice. Oh, yeah. Okay. So this wasn't done. This is not done in the book. As you can see from this chapter, it's not done. Like they don't show that this is this is the union of E can be constructed from these sets and that the sets are disjoint. So that's what I'm gonna do. The library makes me drool. I wish I can afford. It's like some of these books I don't have, and I wish I had a hard copy. Like this book right here, the Rudin Real Complex Analysis. I think that's like $200. It's just too much. It's too much. You got my favorite books here. What's your favorite book? Nonlinear Dynamics. Yeah, this is like everyone's favorite book. Like everyone loves this book. And the physics books you saw, Griffiths, E&M. That's what I have here. I need this library. I mean, if you guys can find this online. You can find a lot of these books online. I found them online. But if you guys ever want some of these books, um, they're not all great. Like they're not all in good PDF format, but a lot of these are. Um, just let me know. Mathematical statistics. I'm currently actually working through that. Um, the books that I'm reading so far aren't. They're not the best. I think the way they define things and stuff like that is a little bit too loose and fast, where it presents like difficulties when you want to prove something. But yeah, I'm working through this book right here, which is a mathematical statistics book, and I'm supplementing with this book right here, which is another mathematical statistics book, and oof, and this book here. So with all these three combined, I'm trying my best to like make it a little bit more rigorous, but not too much. I'm not putting too much effort into that, but I am going through it. Ooh, a hardback. Yeah. I try to get all the hardbacks, to be honest. I only get a paperback if it's the only copy, because the I just don't like how just the potential of the binding to get folded is just drives me nuts. Too much manifolds and topologies. Having a mental breakdown. How is that class going? Any updates? Hmm. And and x is rationally equivalent to itself. Should I say this, or should I say that A is a... No, I'll just say this. X is rationally equivalent to itself. Since rational equivalence is an equivalence relation. X is in X is in A for some A in here. Thus, X is in the union. So E is a subset. Okay, that's the first direction. I want an A minus. E is equal to MC squared y minus with B. That's all you need to know. Truly. L equals I omega. Okay. Now I gotta prove the containment in the other direction. So let X be in the union. I think this is kind of trivial. And X is in A. For some A in here. I feel like I gotta define this a little bit better so it'd be more easier. Okay. So set for each. That's subset of E. Okay. That's part one. And now I gotta show the disjoint somehow. Let A and B be in A. Okay, I wrote this not correctly. A, B, it's not arbitrary. Hmm. A not equal to B? I think this is all we need. I think that's all we need. Okay. How do I show that the intersection's empty though? Maybe I could do this through a contradiction. Let's suppose the intersection um, is not empty. Then there exists an X and A So there exists an element X in A and in B. Therefore, for every Y in A, X minus Y is equal to P over Q for P and Q and Z. Similarly, okay. I should just all write it all in one sentence here. Nah, I'll just do two. Whatever, doesn't matter. Similarly, every z and b, x minus z is equal to u over v, for u, v, and the integers. Okay. And then what we have here, so this implies x minus y minus x minus z is equal to z minus y, which is also equal to p over q minus u over v, which is equal to pv minus uq all over qv, which is, okay. I need to rewrite the order of this because this is what I mainly wanted to show here. So we get z minus y z minus y is equal to this, and then so since qv is in the integers, and pv minus uq is in the integers, holy moly, z is rationally equivalent. So z is rationally, so we showed that z is rationally equivalent to y for every z in a, for every y in a and z in b. But this is for all, right? For all y in a and z in b. But a doesn't equal to b. But a doesn't equal to b. I'm not sure what grammatical syntax I need here. I'm going to assume it's a semicolon, a contradiction. Thus, a intersect b is empty. Hey, I think this is good. I think this is fine. I would cry if I went back to math. You don't have to go back to math. Math is only Math is let's see, how do I type this out? You don't have to. Um, I still haven't used y equals mx plus b in real life. Oh man, I didn't even put the equal. They put minus. I'm a troll. The classic. When am I ever going to use this in real life? Okay, I think that was good. I'm still a little bit. I'm still a little bit uneasy about the way I define this. Maybe I'll look into it later, but I think it's fine. It's just the wording that I have a habit of like constructing the wording so it's not precise enough. It like means something else. Okay, so we just showed this. Okay, let's write down the Vitali example. Okay. I'm gonna put it on the next page. Result 2.48. This is a non-measurable set. I will get a second opinion about the way I defined E, unless anyone can see. If anyone is like familiar and knows, anyone wants to give me some feedback on the way I define the set E in terms of the rational equivalence sets. I will get a second opinion otherwise from somewhere else. Okay. So what does this Vitali theorem say? It says if E is a set of, okay. If E is a subset of R, which the outer measure of E is greater than 0, then there is a subset of E. that is not measurable. Okay, here we go. I'm gonna leave the proof of this one up, but I'm not gonna run through this version of the proof, although they're still pretty much the same. I'm gonna go through the older edition because it references a lemma that is in the older edition, and it's kind of loosely explained in this edition. Proof. Okay, so what do we have here? So let E be a set of real numbers. Okay. So by the countable subadditivity of outer measure, we may suppose E is bounded. We may suppose E is bounded. Okay. I'm barely at the start of this proof and I'm already getting stuck at the first argument. By the countable subadditivity. Okay, what does this say? In view of the countable monotonicity of the measure, possibly replacing E by a bounded subset. What in the world? Okay. Oh my. No, not big using that. Let's see. Why this? Monotonicity. Let's see how to measure. They're they're referencing this. Perhaps you can do it for unbounded cases. Let's see. Where is this at? Oh, but this term is literally referencing bounded and measurable. This is referencing measurable. Maybe not. I think it's fine. Yeah, I think we can assume that it's infinite. Yeah, I think we can. So let's just run with the logic. Oh man, this is so makes me uneasy. By the axiom of choice, there exists a choice function no, that's not the choice function. There exists a choice set. Okay. So we claim that this choice set is not measurable. Oh man. So this CE is this is a choice set CE comprising exactly one member in each A in this set right here. What's the square root of 564? The square root of 564? I could do that. The square root is 564. Let me see. Yeah, I'll figure it out for you. There you go. Don't ever say I never done anything for you, Peps. So this is choice. So that's a choice set. So basically, this is the axiom of choice. Basically says that we can basically pick an element in each set, right? So that's what this is saying. We can choose one element in each set of subsets of sets. And so all right. Let's see. So CE is a subset of X, a subset of E, because it's basically containing elements of. Okay, so I just did this. So by result, what was the result? It was just this one, right? 47. E is equal to the union. So CE, the subset of E. Okay. Okay, we claim that CE is not measurable. So suppose it is. Oh, how you doing, Babs? You work today? Bounded. Be any bounded. Oh, I slept in and went to Costco and Wally World. The hell's Wally World? Your hair's so long now. Yeah, I need to cut it soon. I was thinking about cutting it today, but I didn't cut it. Maybe I'll do it next week. Me? I slept in a little. I did some dishes, showered, and then I streamed. Let's see. Set of rationals. A Walmart. Is that what people call it? Wally World? Because of the wall? Wait, why is CE measurable? Oh, we assume C is measurable. So CE is measurable. Okay. Never cut hair. And again, phase will handle things. What's and again? Oh my. Am I really gonna have to do all this again? The fro suits you? The Jufro? I don't like froze. I can't stay with it. See. Okay, I think what I can do here, so I can show a disjoint. Note. This plus CE is a set of disjoint sets. Since the difference of two elements in CE are not rational. Equal to Y, X is in A, and Y is in B. For some A, B here, and A intersect B is equal to the empty set by the result that I just proved. 2.47. Anagen is the growth phase of hair. Once the anagen phase is complete, return to anagen begins. The follicle detaches from the nerve and the new hair pushes out the old hair. I see. Interesting. Chia pet. Oh my god. Okay. So I basically showed that these are disjoint sets since if X and Y are in CE, okay. Lambda is countable infinite set of rationals. You're a rational? Why, thank you. Oh man. I don't know why I decided to do this today. What are we doing? I'm doing something. That's what we're doing. This is probably the section that makes me the most nervous out of the whole topic because it's so weird. How are we getting along? Just got back from my walk. We are in the middle of Vitali, and it is challenging for sure. Trying to fill in some details. Okay. Um. So not the wiggly buff arms. Oh, man, I need to show that this is disjoint. Okay, these two. What was I trying to say here? Since this is a set of disjoint sets, since I think I forgot something here. X. Oh no, that's the conclusion. I wanted to write the conclusion here. Implying X minus Y is irrational. And oh my gosh. So we got x minus y is irrational. Okay, I need to make this conclusion at the end because the flow of the sentences are a little awkward. Note that if x and y are in the C sub e with x not equal to y, x is in A and x is in B for some A, B, and fancy A, and A not equal to B. Instead of and, I'm going to write with. Note that with x and y in this set, x not equal to y, you were too distracted by these specs. Oh man. Okay, I think this is fine. Irrational. Furthermore, for each x and e, there is a c in this set such that x is equal to c plus q. Or we can just write it x minus c is equal to q. Okay, So lambda 1. So for any there is an x1, this is an x1 in here, and x2 in here. So x1 is equal to lambda 1 plus c1. x2 is equal to lambda 2 plus c2. Or c1, c2 in E. Okay, and how do I want to show that disjoint? So x1 minus x2, which is equal to lambda 1 minus, or lambda 1 plus c1 minus lambda 2 plus c2 is equal to lambda 1 minus lambda 2 c1 minus c2. Okay, that's where the disjointness comes from. Since C1 and C2 are in here, C1. This is too hard. Okay. C1 and C2 are in CE. Holy moly, man. Lambda 1, we're assuming lambda 1 is not equal to lambda 2. I need to write that down too, actually. Oh, I think I know. Okay, yeah, so lambda 1, lambda 2 have to be different. just never equal to 0. I think we just have to show that x1 and x2 are not the same, or they're never the same. Wait, no. Yeah, we have to show they're different, but this could be 0, I think. No, it's never 0. And this is because C1 minus C2, even if they're the same, lambda 1 minus lambda 2 is not 0. And if they're not the same, C1 minus C2 are irrational, so you can't get 0 either way. Is it rational? By the above argument? I think I did this already. Yeah, by the above argument. Lambda 1 minus lambda 2 plus C1 minus C2 cannot be 0. Right, because you can't add a rational and an irrational and expect to get 0. So, and then this basically shows that the sets are disjoint because they're never, if we take a lambda, if we take different lambdas, we're gonna always get different values of x. Okay. A lot of stuff in that little paragraph. Um, okay, I think the boundedness is going to be an issue here. I got the disjointness. I got the disjointness. I have to show E is contained in the union. Hmm. Okay, I need to show that the measure of the C is 0 somehow. This one relies on boundedness. Any set of real numbers. I mean, you can construct it for a bounded set, right? But it says any set. Oh my gosh, this is like annoying. Let's see. Okay. Is there a way for me to do this without boundedness? Hmm. This is bothering me. What is that? Learn. I'm stuck. I'm stuck. I need to figure out how to get unstuck. The proof the proof is fine if it's a bounded measurable set, but I'm not sure why we can force it. Not sure why we can force the bounded measurable set. Because the theorem says for any set, any set of R. It doesn't say it's bounded. And it says that the measure is also positive. So why is bounded forced here? I was trying to do it with unboundedness and see maybe it would work out in the end, but I need to force CE to be 0, and I can only do that. So I can only do that right now if it's bounded. If it's bounded, I can force it to be 0. But it being bounded is actually going to depend on E being bounded. Hmm. It has to do with countable subadditivity. For some reason, that is giving you boundedness, but it's like not intuitive. A countable monotonicity of outer measure by possibly replacing E by a bounded subset of positive outer measure, we may assume E is bounded. So even if it wasn't bounded, we can replace it with a bounded set. There is a bounded set in E that is also positive. Okay, that's fine. So I think this is what it's saying. I think it's saying that if E is unbounded, if E is unbounded, there exists a bounded set. Like call it E prime or something. We'll call it E sub j. A bounded set E sub j that's contained in E such that E is equal to the union of the EKs, which tells you that the outer measure of E is less than or equal to the sum EKs. What's up, E? What's up, Paps? And so since this is assumed to be greater than 0 by the hypothesis, it's not guaranteed to. Okay, so the order of the logic is a little bit weird. So E is unbounded. There exists a bounded set EJ. It's a subset of E such that it's contained in a union and the measure of that EJ is also greater than 0. And this is by this. This is by this. This is basically because like the partial sums, right? It's possible that the it's possible that some of the terms can be 0. They can have 0 out of measure, but because the measure of E is greater than 0, that means there has to be one outer measure that's non-zero. So we have this EJ, which is greater than 0, which is bounded. Okay, I think it's just creating the existence of a bounded set that's contained in E. So if E can be a bounded set, but if it's not a bounded set, then there is a bounded set in E that also has outer measure that's greater than 0, and then the rest follows. I think that is what the theorem, the proof is trying to say. Okay, I'm gonna put this in the top. If anyone agrees, let me know. If anyone disagrees, please let me know. Because I've never been so I guess so uncertain about this. That's what I'm saying, Pabs. Okay. So we basically show that there's always existing a bounded set. Uh, so there exists. So the theorem is for any subset of R, but the idea here is that there's a subset of E that's not measurable, and the idea here is that if E is bounded, then we can apply the logic here, which I'm going to finish. If E is not bounded, then there is a subset of E, which I call EJ, that is bounded, and then there is going to be a subset um, of this, and since this is a subset of this, it's also a subset of E, and that is also going to follow the same logic. Yeah, I think this is correct. So I need to reorganize my thoughts here. I hope that makes sense. Because the end result is we're just trying to show that there's a subset of E that is not measurable. And so this is the case even if E is unbounded. So if E is unbounded, so first we have to start with the hypothesis. Let E be a subset of the real numbers with this measure. And then oh my. Yeah. Oh no. There's too much stuff and I don't want to crop. I'm gonna put this right here. Let's put this a little bit lower. Right here somewhere. Okay, let E be a subset of R without a measure greater than 0. If E is unbounded, there exists a bounded set EJ such that E is equal to the union of EKs and EJ is greater than 0, and this is a consequence of subadditivity. So if E is unbounded, consider EJ. Otherwise, consider E. Okay, and then the logic flows from there. Okay, I'm running out of room here. Yes, I'm so happy this is actually working. Okay, I'm pretty confident I figured that out. It seems to make sense in my head. Okay. Okay, so the axiom of choice gives us the choice sets CE. So this theorem is dependent on the axiom choice, if it's true. And then So we claim that CE is not measurable. Suppose that it is. So the assumption here is that CE is a measurable set. And so when we say CE, we're talking about the bounded version. So we're either talking about EJ if E is unbounded, or we're talking about E itself if it is bounded. And then we want this lambda to be a bounded, countable, infinite set of rationals. Note that for each x and y in CE, with x not equal to y, x is in A and x is in B. For some A and B in this A set, which implies that A intersect B is empty by the result that I proved above. Implying that x minus y is irrational. Do I have space for this? Yes. Furthermore, for each x in E, there is a C in this C sub E such that x is equal to C plus Q, where Q is irrational. And this is just the definition of, this is how we defined the equivalent sets earlier. And I'm trying to show that this set below is disjoint. So we pick any lambda 1, lambda 2 in the lambda naught set with lambda 1, lambda 2 not equal to each other. And so x1 is equal to this and x2 is equal to that, just by the definition of set translation, where C1, C2 is in CE. And then we get this relationship between x1 minus x2, and we show that it's not equal to each other for any C1, C2. So since if C1 is equal to C2, then lambda 1 minus lambda 2 is not equal to 0 because they're not equal to each other. If C1 is equal to C2, C1 minus C2 is irrational by this logic right here. And so this plus this can never be 0 because you cannot add a rational and an irrational and expect it to be expect it to go to 0. So this is a disjoint set. Okay, we've shown that they're disjoint, which is important. Oh my gosh. Hey Luna, how are you? These are so adorable. The Espeon. Oh, are those Chan's new emotes? Nice. I didn't even know he had new emotes. Renchix explained his complicated order at Wendy's. Not the Wendy's. I have a story about Wendy's. I don't know if there are any Wendy's fans, but it's not a good story. Ugh. There was a time when I went to Wendy's and I ordered a burger and the burger patty was cold. And so it was like so it was cold, right? And then like this was before the the commercial about Wendy's being never frozen or something like that. It's always fresh or something like that. And I saw that commercial and I was like, wait a minute. What about my burger? Ever since then I'm just like Wendy's is a huge liar pretending that their food is fresh or never frozen or whatever they advertised. Because I find it hard to believe it's organic. Is that what they really advertise? That's not what they advertise, you liar. Anyways, ever since then, I always kind of had like a side eye of Wendy's. Relaxing after dinner, spend some of the day prepping and cutting peppers and green onions to freeze and for cooking in the future. Hope you have a good day. Thank you, thank you. That reminds me, I need to cook soon. Right after I finish this theorem, I am cooking. Um, okay, so we got a lot of the hard parts out of the way. And so, um, since E is bounded, since E is bounded and CE is a subset of E, CE is bounded. Um, what you making for us? Making chicken, veggies. I'm gonna make something with turkey. I need a meal prep for the whole week. CE is measurable. Okay, so it's bounded. And what I want to leverage this theorem here. There's a theorem that I proved earlier. So the theorem says that if E is a bounded and measurable, so we're talking about CE instead. If this is bounded and measurable, suppose there is a bounded countably infinite set of real numbers. Okay, it's disjoint. Okay, so we are getting that CE has a measure 0. That's by this theorem. Okay. I don't want to do the argument again for showing that this is bounded, because I did it in that proof. It just requires supremums and infimums. So we've shown that CE is bounded, and by the details and result. Did I show it in result? Yeah, the details are in here. I've already showed this joint, and on 2.43, I've showed the details of it being bounded. Okay, this set here is bounded. Okay. And I think I showed this joint somewhere above. Let's show it. Oh, I showed it right here. So I already showed this joint here. Since C sub E is bounded, measurable, and lambda plus C sub E is disjoint and bounded. The outer measure of C sub E is equal to 0 by result 2.43. Okay, that is probably the biggest part of the proof. Did everyone enjoy the extra hour of sleep we gained recently? Sure. I was awake for an extra hour longer. Okay, let's see. Okay, the next part is to show that E is contained in the union. Okay, so note that if X is in E, okay, we kind of talked about it before. Where did we talk about it? Right here. So we're basically exploiting this. X is in so X X is equal to Q plus C. Q plus C. For some C and C sub E. Thus, X is in some Q. Thus, X is in Q plus C sub E or some Q. So X is in the union. And I'm going to rewrite it as, should I rewrite it as lambda? Yeah, I'm going to rewrite it as lambda. I should have used lambda from the get-go. Hence, E is contained in the union. So I'm surprised you aren't already at Unite at this time. No Unite. I played too much of it already. So my result 2.4. The outer measure of E is less than or equal to the outer measure of the union. Put the square brackets. Okay. What's Unite? It's a game that will make you lose your hair. It's what you play when you need your daily dose of rage. Exactly. And this is less than or equal to the sum for lambda and Q. The outer measure of lambda plus CE, which is equal to the sum of just a measure of CE, which is equal to the sum of 0. Which is equal to 0. And I used a lot of results here, so I'm just going to underline. I'll put them underneath wherever I use them. So this was 2.4. This was 2.8. This is 2.7. 2.7 is right here. 2.7, and then this is 2.8. And then it's just the conclusion that I got earlier. And then there we go, we got 0. And this is the contradiction. Right? It can't be greater than 0 and equal to 0 at the same time. Thus, there is a subset of E, namely that is not measurable. Okay. All right. I think that's it. Important maths questions. Give me a second. Okay, I can finally get this out of the way. No and no. I'm gonna be honest. I don't remember the letters, the Greek letters. What is that? Eta? Let's see. What do we have here? Oh, that's Chi? Or how do you pronounce this? It's the best Greek letter. Can't draw the first one. Isn't that just a fancy equal sign? Yes. I know, I can't draw the first one either. It's like crazy how hard it is to draw that one. Like, which ones are notoriously hard? So I think it's see, I like struggling. Now this is like on accident. I don't even know if it looks the same. I can't draw it. Nope. They just get worse every time. Oh my. The thing about this one is that it always looks different every time I try. I mean, they get better every time. You can dedicate a lot of paper to getting it right. I should try. Maybe I should do that. But my handwriting is not even good in the first. Like, I I hate my handwriting. I feel like that needs to be prioritized before getting this guy right. There's also this one. Try to get this. Like a variation of sigma? There's the zeta. I think this is fine. Oh, this is. Ah, man. Oh, I don't know. It wasn't until recently that I started drawing my thetas like this. Oh no, don't look like this. I used to draw them like this. You don't write in cursive, so that's a plus. Reading my own notes can be nightmarish sometimes. Yeah, I feel like if I wrote in cursive, it's like harder to read. I don't even know if I can still write in cursive. I would have to do it really slowly. Oh my. I can't do it anymore. I don't have like the muscle memory. That is how you it's the R is also hard. That is how you right? Jeez. Oh my. Curse. Okay, I got an ellipse. Okay, I can't look at this writing anymore. Yeah. One of these days my writing will be something that I like to look at. It honestly looks better in paper in my opinion, but like on actual paper, but on tablet it's just there's just too many inconsistencies. All right, this is the measurable set stuff. The non-measurable set. So basically we construct a non-measurable set using um, the axiom of choice, right? You first generate a bunch of sets that are disjoint. So the first thing you do is you generate a bunch of sets that are disjoint and contain elements that are rationally equivalent. And so I kind of outlined kind of like the procedure of how to do that here. So rationally equivalent sets, or sets of rationally equivalent elements. So you generate sets that have rationally equivalent elements, and then you can show that the sets can basically generate E, and that each different set, or each set in the set of rationally equivalent. How do I even call it? The worst part is that I can use script to denote new variables because everything I do is basically in script. You can't use. I've debated on actually typing out my stuff on LaTeX because it would look much nicer. But there are moments where I need to draw or do this or do stuff like you probably can't see it because I've highlighted it, which I can also do in LaTeX, but it's just more time consuming. But like stuff like this where I can draw arrows like this one I'm referencing, like this is something that I can't do very easily on LaTeX. I don't even know if it's possible. Cursive is bestive. Do you guys know how to write in cursive? I feel like that's a lost art. Okay. So you generate a set of sets with each set having containing rational equivalent elements. That is this guy. You generate this set, the set of sets, and then you show that it generates the set E, and then we show that for any set AB in this set of sets, with A and B not identically the same, that they have to be disjoint. And so this construction is basically used to create the non-measurable set, because the non-measurable set is dependent on picking an element in each of picking an element in each A in this set of sets. So basically we're picking elements that are not rationally equivalent to each other. And if you do that, you basically create an uncountable set. I write exclusively in cursive, yeah. All cursive letters can be defined by two-parameter function plotted on a polar coordinate system. I kind of remember how to write in cursive. It's been a while though. I vaguely know how to write in cursive, but like trying to do it like on the fly, it would be way too slow because like my muscle memory is just not there. But writing in cursive is faster, right? This is like capital A, right? This is capital A. It's like just a big A. Um, cursive B is something like this. Cursive C is just something like this. Something like that. I don't know the strokes anymore. I would have to relearn them. But obviously I don't write in cursive anymore. Yeah. So we create the unmeasurable set. The unmeasurable set depends on the axiom of choice. So if the axiom of choice is not true, then the argument of the unmeasurable set falls apart. I love writing in cursive. Ren is writing hieroglyphics. So yeah. All right, awesome. Okay. I think that's where I'm going to end it. I got to do some cooking. I got to do some other things. Let's see. Any math streamers? Isn't Penn Center supposed to stream soon? Oh no, my study buddy has to eat. Wait, did you ask me something? Uh, yeah, are you streaming? Are you streaming soon? I remember you said you might stream later. Puck Center has better stream soon. Just big fan. Let's see. Oh, I had to cancel abstract algebra because I needed to tutor. I see. Okay. Any recommendations in the chat? Any recommendations? Oh, inner product spaces. That's the good stuff. Let's see. No, there's no math streamers. No. There is someone doing topology. I don't know who they are though. Pickleberry Math 12. Anyone know Pickleberry Math 12? Oh, looks like Unstucky does. And Stooky. I forget it's Stooky. Oh man. I need a freaking. See, and Stooky's there. So let's go raid. They're doing topology. I love topology. So give me a second while I copy the name. And let's go say hi. Okay. Anyways, thanks for coming and watching me struggle very hard on this. I hope it made some sense if you guys were interested in this. We finally went over the unmeasurable set. It's just a consequence that's needed for to basically to show that not every subset of R is nice. It doesn't give you countable additivity. This is the main reason countable additivity um, isn't free. But Lobster learned new stuff by lurking. Thank you for stream. Thank you for hanging out. I'll see you guys next Friday, hopefully. Hopefully I'll stream 3 days next week. Enjoy the rest of your food and hope everyone enjoys the rest of their day and night. Thank you, thank you. You too, Luna. See you, Babs. See you, Pan. See you, Vicey. Nylon Co. See you later. Take care. Maybe I'll get a haircut next week.